This video is a demonstration of a new, unique network platform called Magnet for Groundwater Modeling. Magnet allows zooming to any location in the world at any spatial scale to simulate, analyze, and visualize groundwater conditions in the subsurface. Magnet allows creating, live and almost instantaneously, a preliminary framework model using existing preprocessed big data stored in a global spatial database. This framework model can be further customized, refined, and extended by users based on their local data or experience and expertise. Magnet drastically reduces costs, allowing users to really focus on modeling, especially iterative conceptual modeling and problem solving. We show Magnet's unique capabilities with a concrete example in northern Michigan. We picked this area because it contains the largest contamination plume in the state. The goal is to understand flow both at and around the site. The model is less accurate near the boundary because flow in or out of this preliminary model is not allowed. So we begin by modeling a large enough area to minimize the impact of the no-flow boundaries at the contamination site. You must sign in or create a user account to submit a model for simulation. This initial submission tells Magnet to create a preliminary model within the box. As your request is being sent to our server, you can note the progress in the status bar. To complete the simulation, Magnet automatically extracts preprocessed big data representing the land surface within the modeling area. These data can be used to simulate the drainage effects of rivers, lakes, wetlands, and seeps. And although groundwater occurs underground, it is actually the surface features and seeps that control the natural system dynamics. When the simulation is complete, the results are automatically output to the mapping display. Head contours and groundwater flow velocities illustrate flow patterns. For each simulation, a series of graphical analyses are automatically generated, including cross-sections, a 3D surface plot of the water table, and a mass balance chart. Note that this preliminary model simulates groundwater flow in the shallow, unconsolidated sediment. Digital elevation models, or DEMs, provide the complex aquifer top surface. The aquifer bottom surface is a constant, computed from elevation information in the DEM. This preliminary model uses placeholders for other inputs, like hydraulic conductivity and recharge, which can be modified. Here we can see that the source of water to the model, the recharge, is balanced by surface drainage. Drainage occurs where the water table intersects the land surface. Now I am telling Magnet to display the spatial distribution of simulated surface drainage. You'll note that this is generally consistent with the distribution of surface water. For example, the model simulates seepage in the Grand Traverse Bay and along the Manistee River. By treating the land surface as a drain, we are able to automatically capture the rivers, streams, and lakes whose water levels or stages are embedded in the DEM datasets. The cross-section shown before can be interactively redrawn at any time, even after a simulation is complete. When the new cross-section is finished, the cross-section graphics will automatically update to reflect the changes. This may take a few moments. As with simulations, you can see the progress of the request in the status bar. A useful application of this model is to release particles and visualize where they go based on the groundwater flow patterns. In this example, we introduce particles to see how groundwater moves away from the major recharge mound in the east and from a system of lakes. This particle tracking technique can be done forwards or backwards, for example, to delineate potential impact areas of known groundwater contaminants, or to identify source water areas for groundwater receptors such as wells or streams. Before resubmitting for simulation, we will make our first model improvement by applying an embedded big data layer to represent the aquifer bottom surface. We also need to increase the time step of the model from the default value of 1 year to about 3 years in order to more easily see the movement of the particles at this regional scale. Note that there are various options for the particle tracking tool not shown here. For example, particles can be released around a well, users can control the particle display size, etc. Also note that the detailed aquifer bottom layer is constructed from hundreds of thousands of water well logs from the state of Michigan, but a less detailed data layer is available globally. More detailed datasets for outside of Michigan are coming very soon. The particle paths are shown as pink lines, emanating away from the recharge mound and downstream from the system of lakes. The aquifer bottom is clearly updated as shown in the cross-sections. Note that the overall flow patterns are very similar as the first model. since both use the high-resolution DEMs to calculate the surface drainage. I will now further refine the model by utilizing embedded datasets of spatially explicit hydraulic conductivity and spatially explicit recharge. Applying multipliers systematically adjusts input values in the data layers by a defined percentage. Here we are reducing hydraulic conductivities to half their initial values and increasing recharge values by 25%. Now I'll resubmit the updated model for simulation. As mentioned before, an embedded layer of hydraulic conductivity is available globally, but the more detailed layers are currently available in Michigan only. The embedded recharge layer is empirically derived based on study of hydrographs and watershed characteristics around Michigan. Currently, there is no embedded recharge layers outside of Michigan available on the server, but they are coming very soon. We can now see the results for the updated model. Again, the overall flow patterns are very similar to the preliminary model, but you can see more variability because of the detailed inputs for conductivity and recharge. To see how these inputs vary across the model, we can make use of our graphical analysis tools. One option is to use the cross-section graphics to show how conductivity varies along the drawn cross-section. This can be done for either the conceptual cross-section diagram or for the cross-section plot. We can utilize the 3D surface plot to show how conductivity varies across the entire model layer. The 3D surface plot can show variations in aquifer elevations, chemical concentrations, and other model parameters. Another option not shown here is to use the Display Settings tab in the Domain Attributes menu. This allows showing plan view distributions of different model inputs or outputs in the map display, including conductivity and recharge. Another useful way to probe your model is to make use of the Nodal Values tool. This tool allows you to click any node or grid intersection in the model to view input and output parameters, including conductivity and recharge, simulated head, and simulated velocities. Note that multiple locations could be flagged at once. Simply click on a flag to show details at that node. We can clearly see how recharge varies across the model domain by looking at the nodal values at different nodes. You may be wondering, does this model reproduce real-world conditions? We can use Magnet to compare simulated head to measure water levels. High-density water level data are available on the Magnet server. They are collected from water well records created at the time of well installation. We can filter the data by aquifer type, date of installation of the well, or recorded water level range. While these data are noisy, largely because of measurements made at different times, inconsistencies existing between different collection protocols, and locations that can be inaccurate, the massive amount of data helps to understand if the overall structure of the model is correct or if the conceptualization needs improvement. Currently, we have water well data available for all of Michigan. More U.S. states and other areas of the world are coming very soon. You can use the calibration chart to compare simulated head to the extracted water level data. Statistical qualifiers are automatically computed and displayed at the bottom of the chart. The y-axis is the simulated head, and the x-axis is the observed water level. Each point compares the measured to the simulated head for a particular location in the model. Points falling along the 45-degree line are a perfect match. Note that the cloud of data is centered on the 45-degree line. This indicates that, for this scale of analysis, the model does a good job of reproducing overall groundwater flow patterns. As you can see, the calibration plot itself can be customized by adding confidence intervals or moving window averages or changing the data marker size. We will now shift our focus to the local scale modeling of the site of contamination in Mansalona, Michigan.